So I want to study now, we have seen the properties of these electric and magnetic fields, that they have energy, they carry momentum, right? So you understand that they have a physical reality. Now let's write the general solution of the Maxwell equation, right? We have studied particular solutions up to now. In particular, we have studied those solutions that were not time dependent, but now it's the moment that we want to solve the full set of Maxwell equations by using these green function techniques, clearly. As it turns out, it's easier. I mean, it's more or less the same, but traditionally this is done by using the potentials, okay? So let's start from the potentials. You remember that these equations allows us to write, because it's the divergence, the vanishing of a divergence means that this B field can always be written as the curl of another field that we already know, and that we call the vector potential, right? Now, if you see, then, okay, this is always true, because this is always true. I mean, this is true no matter whether the field is changing time or not. On the other hand, you remember that the scalar potential was introduced by exploiting the fact that the curl of E was vanishing, right? Because the curl of a vector vanishing means that this vector is a gradient. But now you see that this is no longer true because of the Maxwell equations. It's not any longer true that the curl of E vanishes. In fact, the curl of E is equal to the partial derivative of B, right? But if you put for B this result that is always true, you get the next best thing, because you see, it's not true that the curl of E vanishes, but it looks like the curl of E plus dA dt, that vanishes always, okay? Because you replace B by the curl of A, then you switch around this time derivative and the curl, hoping that there are no singularity around, making that ill-defined, and therefore it's not true any longer that the curl of E vanishes, but the curl of this combination of E plus the time derivative of the vector potential does vanish. And therefore, is this quantity that is the gradient of a scalar. Let's put the minus as we did before, okay? So you see that now, if you study the scalar and the vector potential, to get E is not enough to take the gradient of the potential, but you have this extra term here, so you need both. You need the scalar as well as the vector potential to obtain E. Okay, so it's not as simple as it was in electrostatics, but really it's not that much more complicated, right? And you see, to do this, we use two of the Maxwell equations, so we still have the other two, and the other one is this famous Gauss law, right, that the divergence of E is equal to the charge. But E for us is this, right? E for us is this, so I get the gradient of this minus, the divergence of this minus the gradient minus the time derivative of the vector potential. These things is equal to this rho over epsilon naught in the international system of units. So that is the other well, we can now, if you take the divergence of the gradient, so let's do this, right? Is the Laplacian, so this is the first term, and the second term, again, we can switch around, so it's minus d dt, the divergence of A. So this is equal, and this is the. So this is what the Gauss law gives us when applied to the potentials instead of E. How about the other? You see now 1, 2, 3 of the Maxwell equations. What about the last? The last one was this C square curl of B, to go back to the minus dE dt, right? This combination was 1 over epsilon 0 j, going back to this international units. Okay? And again, I have to replace B and E by this. So B, well, by this and this. To write I want to write the Maxwell equations in terms of the vector and scalar potential. So let's do that. So this is C square, the curl of A, right? Minus the time derivative of E, and E is that stuff over there. So minus gradient of phi minus dA dt. So what is this? So this is the usual, is the curl of the curl. So I can never remember this, is the gradient of the divergence minus the Laplacian, I hope. So this left-hand side altogether is this. So I have a C square, right? So I have minus C square. Let's write the Laplacian that I like here, right? This is minus. Then plus this term here. So plus C square, the gradient of the divergence of A, plus, you see, minus minus become a plus, so plus dt, gradient of phi, plus, now here you have the derivative twice, so plus the second derivative of the vector potential with respect to, and all this is equal to this j. So this is the other equation. And it looks complicated. Okay. So I have to solve, so if I solve these two equations, then I've solved the Maxwell equations, right? But you see, they are complicated, and the main reason why they are complicated is not as much because of this Laplacian and all stuff, but because they are coupled. You see, to solve the one for phi, I have to know A, and vice versa, to solve the one for A, I have to know. And from our experience with differential equations, if they are coupled, it's complicated. So let's see what we can do. Now we go back to an idea that I introduced earlier, that is this thing with the gauge invariance. That tells you that if you change your vector potential A from A to A prime, defined by this, so you introduce a scalar function, I call it psi, okay, by this shift. So this is a transformation, right? I transform my vector and scalar potentials according to this rule. I go from A and phi to A prime, phi prime, and this psi is just an arbitrary scalar function, okay? Now this transformation is called a gauge transformation, and what we already discussed is that if you do this in the potential, you get the same E and the same B field, right? Why? Because you get exactly the same Maxwell equations, right? In other words, if you do this gauge transformation, remember that E is and B is equal to this, right? Now I don't remember if we did this homework or not, that if I do this transformation, I plug in here, I get the same E and the same B. Did we or did not, we not? No, then this is for you. So is that clear? You take, you replace here the primes, right? You plug in these, I mean, it's one line to prove it, and you get exactly the same E and B. Okay? So that's why it's called gauge invariance, because I can reshuffle these fields by this transformation, and I get the same E and B. And since I do not measure the potentials, but I measure the fields through the Lorentz force, I get the same physics. So this is an invariance of the world. It's an invariance of the equations describing the world. Okay? And if you don't believe me, just check, and then on Monday we check together. But let's take this for true. Then you see that this allows us to, we can always change the vector potential and the scalar potential in such a way that this equation is satisfied. Meaning that you start with an A and the phi that do not satisfy this equation. You can shift by introducing this scalar function in such a way that this, at the end of the day, this equation is indeed satisfied. Do you see that? It's just a matter of picking the correct psi. So this is another homework. I mean, there are micro homeworks. It's not that you are that now you have to spend the weekend. It's like 5 minutes. So again, you plug in the shifted, and you will see that if psi satisfy this equation, that is the same, almost. Well, if psi satisfies an equation, otherwise there is no homework if I write that. If psi satisfies a certain equation that you are going to verify, then this is always satisfied. So you can always find the gauge, that is this function, in such a way that this, the new A and phi fields satisfy that, okay? That's the idea of the gauge invariance. You reshuffle your potentials in such a way that some additional condition is satisfied, okay? But now you see that if this is true, you see that now here you can replace, because now in this gauge that is called the Lorentz somebody the homework is okay, this is this, and this one is to find what condition your psi function must satisfy in order for this to be true. Okay? And since psi is arbitrary, you can always find the psi that allows you to fix the gauge in this way. If your A and phi, if your vector potential and scalar potential satisfy this equation, this gauge that is particular is called the Lorentz gauge, because this is the gauge that Lorentz decide to work in order to simplify these two Maxwell equations. But you see that if the divergence of A is equal to this, then this equation becomes right. This is minus 1 over c squared d2 phi dt squared equal rho over epsilon 0, right? because in this Lorentz, the divergence of A is just the partial derivative with respect to t of phi. Then you get another partial derivative with respect to t, so you get the second partial derivative of phi with respect to t. And actually, the same happened here, right? Because you see that if this is true, then you can replace in here, you see you get the divergence of A is equal to this term. That term's combined with that to cancel, and then you are left with only this, right? So you see it's a very clever choice of gauge. I mean, this becomes minus 1 over c squared, divergence of phi dt, right? The c squared cancels. You have a minus here, a plus here, so this cancels with this. And you see you are left with exactly the same equation for each of the components of your vector fields. Equal to, not rho, but this mu I think it should be, there is a minus, then c square epsilon naught, right? That is mu, but okay. Because you have a c square, you bring it on the other side. Okay, so now, so these are the Maxwell equations. In the Lorentz gauge. But now you see we are in business because well, first of all, they are the same equation. So if we solve one, we have solved all four of them. Second, each of them is independent. You can solve it for phi, you can solve it for the x component of A, the y component of A, right? And they do not couple, so there is a slightly higher hope that you'll be able to solve it. Maybe here is a good point to stop for a second, to pause, and how about these potentials? I mean, we brought them in, just it looks like a mathematical trick, right? I mean, it's just because the divergence of a curl of a vector always vanishes that we introduce the vector potential, and similarly the scalar potentials. But are they real? I mean, are they physical quantities, meaning that we can measure them, or they are just some artifacts that is useful for us to work with? But okay, up to in classical physics, I would say they are completely an artifact. Because I mean, there is no way to measure directly a potential. Furthermore, you understand that because you have this gauge invariance, I mean, which potentials you are going to measure, because you can always rescale potential. If at gauge invariance, you know, the gauge means that you have a gauge measuring some height, for instance, and you can always change this gauge. So there is no way that this, at the classical level, gives you a physical quantity, right? Because physical quantities, the world does not know about this gauge transformation. This is the thing I introduced here, but I mean, the real world does not know about this gauge invariant, this gauge transformation. So all physical quantities must be gauge invariant, right? Otherwise, Lorentz starts with his gauge, you start with your gauge, you measure two things, and you get two different results. That's clearly not the way the world works. So at the classical level, really the physical quantities are the fields, the field strengths, E and B, or H, D, or whatever you have if you are not in the vacuum, but in some macroscopic medium. And so this is more that it's like a trick. I mean, you use these auxiliary functions. At the end of the day, you use these equations that are wrote there that give you, for a given scalar and vector potentials, give you the electric and B field, and then you measure the force, and that's what you have. However, at the quantum level, there is something more because of this fact that the phase of the wave function sort of fills the space more than a classical trajectory, right? Because if you think at the, okay, I know every time in quantum mechanics you start with this sort of, have you seen this sort of, that you have a source of electron, for instance, right? They go through two slits. You must have seen that because it's compulsory. And then you have a screen, right? And then you have this nice interference pattern, right? So they go through, I don't know, let's call it, I call it this path 1 and this path 2, right? This is the basic of quantum mechanics, they tell you. Because, you know, this is a particle, but when you measure the number of hits here, it looks like a wave, no, that is interfering. Okay, big mystery. But, okay, I don't want to talk about this, but I just want to, if you have a magnetic field here, for instance, put a solenoid in between these two paths. Have you seen that in quantum mechanics or not? Yes? No? No. So if you put a solenoid, so this is a cross-cut. Then I look at the same experiment. I have here some electron coming, and I put here a solenoid, an infinitely long solenoid. So what is the characteristic of an infinitely long solenoid? That inside, we have solved, you have this constant B field, right? But outside, the B field is 0. However, if you compute the vector potential of this field, the vector potential is not 0 outside. The vector potential is everywhere in order to produce this B field inside, if you solve the problem. So the electron here, in a way, it cannot feel the B field because the B field is there and the electron is there. So because we think physics is local, the electron, the guy that goes here or there, does not feel the B field. But however, it does feel the vector potential. Okay? And what happened to this vector potential? Well, if you measure the phase shift, right, this is a question, what is the phase shift of the wave function of the electron, the one that goes through path 1 with respect to the one that goes through path 2, right? And I think this phase shift is, well, is whatever the phase shift is if you, when the B field is not there, right? And I think this is what you have computed. So, I mean, if you call x the distance from an arbitrary point here, this phase shift is something like x, the length, say, d over L, and 1 over the Compton, the Compton wavelength, right, of the particle. This is the interference that you produce because of the phase shift in going from one path to the other. If you have zero phase shift, you don't have any interference, so you have a constant probability of finding the electron there and there. But okay, I don't care about this because but you also have, you see the wave function, if you go this way, gets a phase, so a wave function for the electron in the magnetic field is given by a phase shift that is proportional to the charge of your electron divided by, multiplied by this integral here, the trajectory, right? So you see that if you compute the total phase shift in going from 1 to 2, this must be the sum of the two integrals, right? The integral to go through the path 1, so 1, this vector field, minus, because now you go back, actually it goes the other way, but I want to close this, minus q h bar a dl along the path 2. But what is this term? This is the, right, this is the, because this goes this way. This is the circuitation of A going around. And what is the circuitation of A going around? Is the flux of B, right? So this is Q over H. If I call S this, is the flux of B across that. So this is different from 0. And you see that because this is different from 0, even though the electron never goes there, but simply because it picks up this phase shift because of the presence of the potential, the vector potential, you get an extra phase shift. So you will see some disturbance in this interference pattern when you turn on the B field here. So that tells you that in these situations, you see, you are measuring the vector potential in a way, because here you only have the vector potential, not the B field. I mean, it's true that that is proportional to the flux of the B field, but locally there you only have the vector potential. So this effect has been measured. It's an experimental fact. It goes Bohm-Aharonov effect, and is the fact that at the quantum level, the vector, the potentials of the electric and magnetic fields, they have sort of a physical reality, because their presence shifts the interference pattern that you measure in these typical slit experiments, the two-slit experiment. Okay, so this was an aside, because we do not do quantum mechanics, but it's good to know. So interactions that are invariant under gauge transformations, like Maxwell equations, like the electromagnetic intensities, are called gauge interactions. Okay, and as you probably know, most of the interactions we know. How many interactions do we know? I mean, how many fundamental interactions do we know? You know, the electromagnetic, gravitation, right, that we study together, and then two that we did not study together, that's the weak and the strong, right? And all these four, okay, let's not talk about gravity, that is complicated, but the other three are gauge interactions. They are interactions that are invariant under gauge transformations, okay? So you see, it's very important. I mean, this is from a curiosity, from a trick that Lorentz pulled out from his hat in order to decouple Maxwell equations for the potential, became the basis of our understanding of all the interactions. So you see, he was just solving a homework in a way, and then he discovered without knowing, because he died before this became clear, but yes.
What does gauge mean?
Gauge. A gauge, you know, it's like in English is if you have something that measures height or levels, that is a gauge. And as I said, this is like here, because you fix the level at which you start measuring your A and phi field. So that in that sense, it doesn't matter where you start, so you talk about gauge invariance. So a gauge, if you go in the broiler room, where there are all these things that tell you how much heat is there, that is a gauge, right? Okay. Yes?
If we say at the quantum level that potentials are physical, then how will we explain the gauge invariance of the potentials?
Well, as I said, then they are physical, but all the interactions are gauge invariant. So. No, but you see, in fact, it does not depend directly on the A field. It only depends on this circuitation of the A field. And the circuitation, you see, happens to be the B field. So you see, at the end of the day, it does not depend. This quantity is still gauge invariant. So yeah, I'm stressing a little bit the meaning of physical reality, because at the end of the day it's the B field. But the important point here is not, okay, if you don't have any B field, then there is no effect. Because you can think of gauge configuration corresponding to 0 E and B fields, right? So if that is the case, you don't have any physical effect. But the point here I wanted to stress is that locally, in the point where the electron goes, you don't have a B field there. You just have the potentials. But it's true, as you said, that at the end of the day, if the gauge configuration is a pure gauge, they're called, so gauges in which the E and the B fields vanish, then you don't have an effect. But you need the gauge potential. So you need this potential to explain locally. Otherwise, you have to assume that there is some sort of instantaneous, at the distance, interaction between the B field and the electron that is there. That's a possibility. But the general philosophy of field theory is that everything is local. You don't have this sort of, that's how people explain this, that you have this, that there is some leakage of the B field that the wave function is filling, and that's what is, but this doesn't seem to be the correct explanation. Okay, but okay, so let's see how far we. So now we have to solve these equations, right? There is no shortcut here. We have to, okay, pull up our sleeves, but okay, you can pick the one you prefer, right? It doesn't matter. In fact, let me call psi either phi or any components of the vector potential, because you see they are the same equation. So if I solve that, I've solved all of them. So let me solve in general this equation here. Let me call psi. Now this psi is not the gauge function. It's just any scalar function. Psi minus 1 over c squared, the okay. And this is equal to the source here. Now, because there are many 4 pi's going around, let me call the source any function of r and t. Okay, so this is the source. Let me pull a 4 pi because I always get 4 pi's, and that's actually the reason why the Gauss system is nicer than the international system. But okay, it doesn't matter. Let me put 4 pi. So this is the source, and this is known. Okay. I know the source. I know there are charges somewhere, some currents. They are varying in time or not. I don't care. I take the most general. So the system of charges and currents is given. What are the electric and magnetic fields generated by this generic distribution of charges? No, this is the question that Maxwell equations answer. If you have solved that, then you go back to the first class that we had together. You know E and B, and you plug into the Lorentz force, and you find how these charges move under the influence of these fields. Okay, this is the general idea. There is nothing more, but also nothing less. So for the moment, we in fact, the Lorentz part, we already sort of discussed it, even if very briefly. We won't come back to that. But now we want to, given a generic distribution of charges and currents varying in space and time, what are the generated electric and magnetic fields, okay? The component of which are represented by this psi function here. Okay, that's a standard problem in mathematics, because, you see, if I take this equal to 0, this is exactly the problem that we already solved in electrostatics, right? Because this is the Poisson equation with this normalization and without this t. So we just generalized this discussion of the Poisson that, remember, in general was solved by the green function. So I want to define the green function for this problem. But first, I want to do a Fourier transform. I don't like this fact that it depends on R and T. I rather use Fourier transform to transform this equation to a nicer form. And how you do that? Well, you already know that if you have a function of space and time, this can be Fourier transform, this is just a normalization, into a function psi of, well, space I leave it alone. I could Fourier transform everything, but I do not. I Fourier transform just time. So now this, it depends on the frequencies. And this is an integral over the free, right? This is the Fourier transform. You're familiar, right? Ah? You don't, what? What's, if this is the Fourier transform, I can also Fourier transform my source, right? What? You want a square root there? You're not going to have it. It's a constant. I mean, it depends on the normalization, right? So I'm lazy. I don't want to put the square root. It's still good. Do you remember why the Fourier transforms are useful? Yeah, why do we go through the trouble of introducing a Fourier transform? They must be useful, because otherwise, in physics, you rarely do something that is not useful. And physicists are very lazy. So it must do something to a differential equation. I told you during several times last year. No. You start, you have a differential equation, right? And we don't like differential equation, remember? Because they are difficult to solve. One thing we know how to solve are algebraical equations. So the Fourier transform a differential equation into an algebraical equation, right? That we know how to solve. Then, of course, you have to Fourier back, and that's where that's complicated, because there is a conservation of complications. Otherwise, everything would be very easy. So you shift the tricky part from solving the equation to Fourier transform back. That's what we are going to do here as well. But this, you see, is not the full Fourier transform. The full Fourier transform would be to Fourier transform also in space. But we are not ready for that, because we need special relativity to that. Because you see, we are not very, well, in principle I could, but then we would have the problem to understand the space-time in which we are Fourier transforming, and we do that at the end of this course. So let me just do it the old way, that I just Fourier transform in time, where I know what I'm doing, and I don't have to worry about the relationship between space and time, because as we will discover, that is not trivial. It's not simply that space behaves like time. There is a problem with the signs, right? But that's not, it should not be a surprise, because we know that space is different than time. No? For once, you can move back in space, but it's much harder to move back in time, right? So they must have something that is not exactly the same. So space-time, it is more or less the same, but the signs are different. However, if I Fourier transform in time, that equation clearly becomes that where I have this term, I just get, if I call k the ratio between the omega and c, right? I get just a k square here, clearly, because I go to the Fourier space, right? Then I take twice the time derivative. You see, this is become algebraical. Unfortunately, this part does not, because I have not Fourier transform in space. So I hope we will have time to do that in special relativity, where we fully Fourier transform, and then this equation becomes simply an algebraical one. But I think we won't have time. But just bear that in mind. So now this is an equation on this Fourier transform. So maybe I should put a hat, I don't know. Well, it's clear that it's the Fourier transform because instead of having time here, you have this. And this is minus 4 pi, the Fourier transform of the source distributions. Okay? Now, this is a simpler equation than this one. And it's simple enough to deserve a name. These are called elliptic partial differential equations. And you know, you have mathematical departments just studying this kind of equations. Again, if I take k equal to 0, now k equal to 0 in the Fourier space, what does it mean? It does not depend on time, right? If it has, this is called wavelengths, not right? Because if k is equal to 0, that means the Fourier space is time independent. Therefore, this is there, and you are back to Poisson equation. So far, so good. Okay, so I want to study the elliptic partial differential equation defined here, and the way to do this is to introduce the Green function. Oh, we have time. So again, you remember the Green function that I call, you see, is the j of k, because there is a Green function for each value of k, right? Is that function that for two given positions in space, right, gives you the delta function. That is exactly like for the Poisson equations, right? So that sort of justify why we spend some time with the Poisson equation, because it's very similar, but of course there is this this point here that makes the crucial, and we can, like for the Poisson equation, let's call big R the actual distance between these 2 points. So you see that, I mean, because of the symmetries, and because there are no boundary terms here in this problem, I'm solving it without. This Laplacian can only depend on big R, right? It's not going to depend on. So I can write this operator like 1 over R, the total derivative with respect to big R, right? Of R, G, R, G, GK, okay? I'm just writing the Laplacian in spherical coordinates, the one I gave you the photocopies, and plus k square, this j of k. So this is still a function of, and this must be minus 4 pi delta r, okay? Is that, you remember what is the phi in spherical coordinates? Is this something 1 over r d r square r phi plus the 1 over r square? This you should know by heart, even though I don't. I have too many phi, but you understand, this is a big phi. And because it can only depend on this, it cannot depend on the angular part, so I only pick this part here, and this is what I wrote here, okay? So this is the equation that we want to solve. Oh, Okay, so you see that everywhere except at the origin, well, it's not the origin, it's the when r is identical to r prime, this green function must satisfy the homogeneous equation, right? Because the delta function is just 0 except when big R is identically 0. Okay, so this equation, is rather simple, right? The homogeneous one, because it's just that R, G, K, right, of R. Well, you record. What is this equation? If
I think when r is r prime, it's not 0, right?
when big R is equal to 0.
Yeah, it's not 0.
When this is equal to 0, this is different from 0.
Yeah, yeah.
So when
When r, yeah. If r is different from r prime, then it is the homogeneous.
so if it's different from yeah, I'm sorry. What did I say?
R
I mean, you want this to be equal to 0. So this is equal to 0 except when, okay? So everywhere else it's the homogeneous equation. Okay? Except in R equal to 0, sorry. And what is this equation? You see, this is again, you know how to solve. This is some combination of exponential, right? Some combination of exponential. Here I forgot this. No, sorry. It's here, right? So you bring this in here, then you see that this is exactly a combination of exponentials. So that means that this combination R, G, K, R should be some A e to the I K R plus B e to the minus K R, right? Now my R looks like a K, but... And you see, when R goes to 0, okay, for simple, just looks at the homogeneous one. For R going to 0, right, that means these are very small coefficients, right?
It's just a phase.
Well, so they go to, so K, this goes to 0. So this, you see, so you only want the solution that goes like 1 over R, okay? Therefore, you have A plus B equal to 1, and the generic solution of this, you can write it here. Well, you can have two, right? You can have the one with the plus sign here and the one with the minus sign. So these usually are indicated plus minus, okay, K, R equal E plus minus I K R over R. These are what they are, you see, they are spherical waves. These are solution. They look like exponential, but they're exponential like with the radii. So they are spherical waves. And one with the plus sign is a expanding spherical wave. Then it's suppressed by this, right? And the other one is an incoming, a collapsing spherical wave. Okay. That this is a solution to this?
No, this from this.
Well, you see, the R is here, so you bring it back here. And then you have two combinations, the one outgoing and the one ingoing. Are two sets of solutions, right? It's like if you have a solution going one way and a solution going the other way. The only thing is that here is spherical. So the general solution is going to be a superposition of these, but what about, so I still have to Fourier transform, right? So if I put, now I put these solutions into the Fourier transform. So it's 1 over 2 pi the integral minus infinity plus infinity e to the either plus or minus kr over r e to the minus omega t, but you see t minus t prime because it's the green function, d omega. So this is the green function plus or minus. Sometimes these are called the advanced and the retarded. You'll see why in a second. That is a function of r and now t minus t prime. So this would be the solution of the, this would be the green function for this problem. Actually, we have two green functions, two possibility of green function. And as I said, the complication is that you have to do this integral. But actually, it's not that much of a complication, right? Because if you remember the definition of a delta function, you see this is essentially, you see this does not depend on the omega. So you have an integral of the exponential minus I to the something. That's the definition of, with even the 2 pi of the delta function. So this integral is just, well, this is 2 pi divided by r, big R is just there, and all this stuff here you see it's like the delta function of t minus t prime minus or plus, depending, of r divided by c. If you put back, you see, because k is omega divided by c, so you pull in inside, you get the switch of this sign, and then you have this. So when you plug in here, you have this 2 pi that goes away. That's if you had the square root. You had to normalize also there. And so you get the delta function of, well, let's write it like this. It's t prime. I switch it around. So it's t prime minus t minus plus r minus r prime divided by c. So I rewrite r as the length of the difference in these two vectors, and divided by big R, that again is r minus r prime. Okay? No? What is missing? So you take this. Now I Fourier transform. So I take this and I put in here. Right? Now I'm Fourier transforming. So where did you get lost?
The last.
This?
Yes, the complete integral.
No, I mean, put k equal to omega c, right?
Okay.
So you see omega multiplies this stuff here, multiplies t minus t prime, right? Then minus, because I pull a minus here, so minus plus r divided by c. So this is this exponential becomes this, right? So then I know that the integral minus infinity to plus infinity of e to the I x dx is equal to 2 pi delta x, right? So, and then I just plug back the definition. R, big R was the distance between r and r prime. And so I have this. So now I have my solutions. I have, let's rewrite it here. Well, I have the green function, then the solution follows from the green function. So I have my green function that I write here. So it's delta t prime minus Now, what was the green function of the Poisson equation? It was just 1 over, right? If you forget about the boundary condition, it was just 1 over r minus r prime. So you see, It's just the difference, you get this extra delta function. This is really beautiful, right? Because it's like the previous problem, right? The only difference is that you have to compute your green function not at the time t, but at this time t prime. And you see why that? You see, these are called the retarded and the advanced, depending on which sign you pick. Pick the retarded one, right? Okay? It's t minus this. This is the time it takes to light to get to the point there. Because you see, say you have some charge moving, and you are looking here, this is r, and that the other is r prime. And you are sitting here, and this charge suddenly decides to go left. Okay? So you're sitting here, you are not going to find out about this instantaneously. Not at the time t. At the time t, this goes left, and you are here. But it takes a time t plus or minus, depending, say, the distance. You see, this r minus r prime divided by c is the time it takes light from here to reach you. So until that information reaches you, you don't know about the fact that the charge has gone left. So that's why it's called retarded. So your green function is exactly like the green function for the static problem, but what you see is the position of the charge at the retarded time, because you only know about the charge after light has reached you. You see how beautiful it is? So it's built in the theory that there is no instantaneous propagation of signals. And therefore, your green function can only depend on the retarded time. So you see here the field as it was produced by the charge at the time t minus r prime divided c, that is the delta t that it takes light to bring you the information. The odd thing is that it could also work the other way, because you see Maxwell equations are completely time reversal invariant. I mean, I can switch t to minus t, and the equations are exactly the same. So it's also true that it would work also that at the advanced position. So that's a little odd. And for this reason, we use the retarded solutions. But in principle, everything is fine because it's time invariant. So in a way, you could build up your green function from the advanced positions instead of the retarded one. In general, we use the retarded one because for the way our brains work, that makes more sense. But from the point of view of the equations, this was also true, by the way, for Lagrangian equations and everything. It was completely invariant. You could switch t to minus t, and that would be still a solution, right? From the point of view of classical mechanics, the proverbial cup dropping down and breaking, and then reforming exactly the same way and popping up, they are two exact, perfectly fine solutions of the same equation. It just then happens that usually things fall down and don't. But to understand that, you need some thermodynamics. And so this is the green function, and you know that if you have the green function, right, now you can write the general solution. So now I can write psi, right, psi r of t, that is the solution of this, I think this equation has a name. Is that the Kirchhoff equation? Well, okay. Well, look it up. But anyway, I mean, the general solution of that is going to be any solution of the homogeneous equation, right? Any solution of the homogeneous equation plus so that's so I call it psi in. I call it psi in because I'm assuming that is some incoming solution. But again, because of this time invariance, it would be okay also to put an outcoming solution, plus the integral over space and time of your green function. Okay, so I take in, so I take the retarded green function of r and t, and r prime and t prime of my source, right? You have to. So this is the t minus infinity situation because it's the incoming. Okay. And actually, because you see that the t part is just a delta function, so there is an easier way to write this solution. Okay, this is whatever it is. Let's take the equal to 0. I mean, it's not going to be. And so everything, I can do the t part of this integral because it's just a delta function. So this solution is just exactly the same as in the Poisson equation case, right? But the only thing is that here I should put some to remember to remind me that this t prime is at the retarded time, meaning that t prime is not the t at which I'm, but is t minus r prime divided by c. Okay? So everything looks like the static case, except that I have to remember that the static case is not the one at the time I'm doing it, but is at the previous time, the retarded time, because that hits me only when light reaches the position in which I am. Is this completely clear, or otherwise I repeat it because it's the most important point, the take home. It's very nice. I mean, it's exactly, so it's not, I mean, you may have thought that it was a complete waste of time to solve the Poisson equation, but actually now you discover that it was not, because essentially it's like before, you only have to remember that the time is the retarded time. And you have solved the full equation, not just the Poisson. Yes?
I want to know why I don't get you about t equal minus infinity.
This?
Yes, you forgot this function.
Why I put it to 0?
Why?
Well, because you see, I can do whatever I want here because it's a blackboard. Well, that is the solution of the homogeneous equation. So it's something that is there before you put your charges. So it's coming from somewhere, from infinity, in fact. When you start counting, t equal minus infinity. Then you have these charges coming in, and they generate this. So I may as well put it to 0 because it's not going to. But maybe you have a plane wave there before you start putting charges. So that is still there. You know, while you were playing, a plane wave comes and passes through. But you just add it, and it's nothing is changing.
If I understand, so here, when you see your Dirac or your, how I can call this? No, the first.
The green function.
Yeah, okay. Yeah, I know. Green function, Dirac
The delta function.
Okay, so you consider for the wave, the wave is coming, or because
The retarded.
because you take for t equal minus.
Yeah, because there was a e to the plus or minus. So one is an expanding wave, and one is an incoming wave. And because our experience is that we have causality, meaning that you explain the present status using the previous one, we take the retarded. But from the point of view of the equations, you may explain the present status with the future as well. I mean, it's the same from the point of view of the equations. Our experience is that it's the past that modifies that determine the present. But in fact, you could even take a linear superposition of this. I could take, for instance, that half comes from the past and half comes from the future. It has been done. I mean, it doesn't matter. It even has some advantages in field theory. But I mean, for us, let's stick to to the one that has an intuitive explanation. So, well, now I can write the solutions for. So you see, we have solved the Maxwell equation, so no big deal actually. And by using this, I have that the vector potential, therefore, at the point R. So the vector potential at the space point. I start talking about space-time because very soon we will talk about that. So at the space-time point identified by R and T is given by, so now is A, so I have mu naught divided by 4 pi, if I did it right, this integral d3R over the volume where you have some current, so prime, J in this volume, T prime, but retarded, right, divided by R minus R prime. So now I'm specifying the source, okay? So you have 3 components, you rebuild the vector potential. Then you take the curl, and you have your B field. Similarly, phi at space point R T is 1 over 4 pi epsilon naught, the same thing, right? Only now you have the charge density R prime T prime, again, retarded R minus R prime. If you go back, this is exactly the same solution of the static problem, and the only difference is that a minus sign. Okay, I trust you. So in general, if you, so I stop here, but let me, so if you are sitting here, right, X, Y, Z, this is the point R. So here you have at P, you have the present position, say, of a charge, okay? So now it's time T, present position of a charge here, and this is R, and you are here. So what do? You compute this, right? But the point is that you compute this by taking J and rho from this charge, not at the present point, but at a previous point, P prime, right? That is the retarded position where the distance between these two is T prime equal to T minus this R prime divided by C. So this is the retarded so yours here, the charge is here, but you compute as if it had been there. Because, you know, whatever it's doing, it takes time to reach you. So what it's doing here, it will reach you, you know, at a later time, when actually the charge will be here.
I think it does seem like for a light from the sun to reach Earth, it takes like 8 seconds, right?
From the sun,
Yeah.
8 seconds, yeah.
So what we see is the one that was before.
Right, that's exactly the same. As they say, if the sun explodes now, you still, no, 8 minutes.
8 minutes.
You still, I can go on for 8 more minutes before we are burned away. Okay. Exactly the same. Actually, well, there is even, yeah, light is 8 minutes. So that's, but you see here is already here is built in the meaning of the Einstein relativity, because light has a finite speed. You see, you have all these effects due to the retardation. And the only further input is this speed the same for all frames of references? Because we learn from classical mechanics that physics is the same if you are at rest or you are moving with constant speed. But here you see it seems that something may be wrong, because what is the speed of this? I wrote C, 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 C everywhere. But But what now if we are moving with a speed v? Should I replace c plus v everywhere or not?
Based on Galilean or Lorentz transform.
Right, so we will have, you see, we are forced to address this problem. Okay, so I stop here, and then we proceed with some more. Now we have the general solution, so we can apply to a single charge, to some charge distribution oscillating in time, that is an antenna, that is what produces radio waves, and then some more. Okay. Thank you.
Thank you.